Myślałam, że coś powiedzą, ale... Good afternoon, everyone. It's our pleasure to have today a talk of Professor Łukasz Wyrzykowski. Łukasz defended his PhD thesis exactly 20 years ago in that given room. Is that right? Yes, exactly.
November 2005.
Yes, so it's a big anniversary for you and for us. And Łukasz, during his PhD studies, was in Israel, was also collaborating with researchers in Manchester. Then after defending his PhD 20 years ago, moved to Cambridge, where he spent 7 years and started to work on Gaia data, and he's working on that data all the time, also with the OGLE data from the very beginning, and recently on a VHTOM system that he's gonna also tell us a bit about. Everything revolves around black holes, right? Especially in your research work, so it's a pleasure. So, listen to your talk.
Thank you, Milena. Thank you all for coming. And as Milena said, this is exactly 20 years ago. I was standing on the very same place, the very same room, and it was equally stressful. So this is it. Okay, so I'm going to tell you about some of the summary of my recent research, and I realized that I haven't given the talks here, the seminar here, for quite a while now, so like 10 years or so. So you need an update from my side. And I need another slide. Next slide. So just to show a couple of faces of people involved. As you know, I'm also part-time employed at the NCBJ. So I'm sharing the team between these two institutes. So the observatory here with Moritz, Joy as PhD student, and then collaborators, mostly Mariusz, Milena, and Monika. And then from NCBJ side, there is Prayer, who's actually here in the room. He's going to give his talk next week. And Priscilla is on her way to Poland. There's some students who've been involved in the project, Chris and Katarzyna in particular. They're postdocs now. Chris is actually back here in Poland. Nada is finishing her PhD. And then many other people from Poland and from outside of Poland, and there's a long list of collaborators there. So these days you don't do things by yourself. I have to mention the funding as well. There's a DINA grant here in the observatory, and there is a European ACME grant in the NCBJ, which mostly funded this work. So it's going to be about black holes as the main theme, but I think, generally speaking, we need to think about stellar remnants as the main target of interest here. And I just remind the Astronomy 101, what do we know where the remnants come from? There are still many question marks here, but at least we think we understand this left-hand side of this plot, that stars, how they are formed, depending on the mass, how they evolve, and then they end up as some kind of weird, or not weird, or standard, non-standard explosions, supernovae, 1As, or core collapse supernovae, and we end up with some a range of different remnants, white dwarfs, neutron stars, and black holes. Where with white dwarfs it's fairly easy. There's this cutoff at 1.4 solar masses, so we know where was the most massive white dwarf can be. But with neutron stars and black holes, there's still ambiguity where these things start and when they end, when what is the lowest mass of the black hole or the highest mass of the neutron star. But we do see these remnants in multiple ways, and I'll start with this. So colliding black holes in a galaxy far, far away, where you have a merger of two black holes, and then they emit gravitational waves. These mergers, for example, this is an example of an 80 solar mass black hole being formed out of two black holes. So we know of these black holes, but historically, these were the first black holes we found in our Milky Way. So where there was a compact companion eating up a star, which was close enough so that then the tidal forces were dragging the matter and forming the accretion disk, which was then revealed in X-rays in particular. So actually, this is another impression of Cygnus X1. I think this was the very first black hole confirmed, and with mass of this black hole here of 21 solar masses. So there is also another way of finding, fairly recent, finding black holes where we also have a companion star in the black hole or an invisible companion, but there is no interaction there. We only trace the orbit of this luminous component, and then we can figure out that there is something massive accompanying this star. So if we plot what we know so far on a quasi-histogram plot like this, I've stolen this one from gravitational wave people. This is not very up to date, as you know. There have been new detections. This graph is still growing, but you see in blue there are gravitational wave black holes found. So first the two components before the merger, and then the final product of the merger. So we can probe fairly heavy masses there. So with the heaviest of about 200 solar masses now. Then there is also a lower end of this distribution where we see neutron stars mergers. These are less common, of course, but they're still there. So we see neutrons colliding, neutron stars colliding and forming either a neutron star or a black hole. On top of that, the other dots, they show black holes and neutron stars as seen in electromagnetic waves, but this is actually only limited to these X-ray systems. So we see that these are the magenta ones are the black holes, where its distribution ends at about 20-something, 21 solar masses, with Cygnus X1 actually there, but it goes all the way to like 5 or a couple of solar masses. And then these are the neutron stars here, found in these binary systems. So this is what we know from these two ways of looking at companions.
Ask a question, yes.
Sure.
Is there any evidence that the orange dots are neutron stars?
Well, we do see kilonovae explosions, right? And when you merge two neutron stars, then you do see that in some of them. One. But then the rest is just a matter of computing the mass, right? Just if the mass is below 3 solar masses.
Basically, the only evidence for a neutron star would be tidal deformation, we don't see, and or electromagnetic kilonova, which we don't see. So I think there is evidence for one, and for other there is no evidence.
Except the mass, right?
Except the mass.
Yeah.
But
so judging by the just mass cutoff, we assume these are neutron stars, but you're right that this is just an assumption. So there's still many unknowns here. But if we overplot, first let's overplot the newest detections with the non-interactive systems. So these are again electromagnetic detections, but where there is no interaction between the compact object and the star. So far we actually know only about 5 systems like this. So there are 4 black holes and there is 1 neutron star from such a system found. And you see the most massive one is Gaia BH3, which actually goes above the cut of 20 solar masses. And I'll spend a couple of minutes talking about this particular system. So this is this is the giant star orbiting something which we don't see, and then this is the center of mass. Using the positional measurements of this star over a period of time, we were able to determine the mass not only of this object here, but also of the mass of the companion. And the companion turned out to be 33 solar masses at a distance of about 590 parsecs, so 30 millipi. So this is currently this is the most massive black hole known in our Milky Way, of course, apart from the Cygnus A asterisk, of course. But this is the most massive of this mass range black holes. And this is also one of the nearest black holes to us. What is interesting about this star, actually we can study the black hole indirectly by looking at the star. And there's an old giant with very low metallicity. And so the metallicity we could measure, and then we assume the black hole also used to share the same metallicity. And then when we found that the orbit of the entire system is actually just temporarily crossing through the galactic disk. When you trace it forward, this is what you see. This is the actual orbit of this system. What is this going to do over the next loads of years? So possibly we figured that this is possibly part of Sequoia halo structure, where there is very low metallicity there. But even more probable, there is a AE2 stream, one of these streams going through the galactic halo with metallicity of -2.6. So these are actually, so this is a remnant of the merger, or minor merger of some dwarf galaxy which happened some time ago, hence this difference in metallicity. So this is actually an immigrant in our galaxy. So this is this companion and the black hole, they came from other galaxy, and now they are settling into our Milky Way. If we plot the three black holes, at least we know from Gaia, then we overplot on a histogram of all the black holes known from gravitational waves. We see some interesting coincidence that BH1 and 2, they coincide with the first peak, and then BH3 coincides with the second peak. But this is still very preliminary, just very small number statistics. But this is kind of the first evidence that we start to see maybe we're probably more or less the same populations as seen in gravitational waves and electromagnetic systems. However, the most interesting black holes they look like this, right? So there is no interaction, there is no companion star, there is no X-ray, there is no gravitational waves emitted at all. So there is no other star which could reveal the presence of this through the interactions with the orbit. So of course, in this very room, we don't have to advertise too much, but this is the way to find them. So gravitational microlensing is an animation showing black hole passing in front of a star from the background, and then the star is temporarily getting brighter. So the only feature, only parameter which is changing of this star is the intensity, color, and other doesn't change. But we also know that this phenomena, so apart from the change in brightness, so this is the source here entering the Einstein ring, we see the images, so the source is getting brighter on a time scale of weeks and months. But on top of that, there is also change in the position of the source. So this is the source as if it was not lensed at all, and this is the actual position at the center of light of these two images we can trace over a period of weeks and months or even years. However, the angular separation of this change of the position is of order of milli-arc seconds, right? So this has been the main challenge. That's why the microlensing has been done over the last 30 years, primarily focusing on photometry, just obtaining long-term and large-scale photometry with surveys in particular by Ogle and others. But this is a new avenue, which is very important, because only if we see, when we only see the brightening, we know that something has been lensing something. We have no idea what was the reason for the lens. If we combine, if we obtain the measurement of the positional change and combine these two measurements, then only we can solve a microlensing event, and hence derive the parameters like distance to the lens and more importantly the mass of the lens. And this has been achieved only once so far in history. And this is the object found with microlensing. So this is the Ogle 110462 object. And I placed it on this chart again. And this is a zoom in. This is the visualization of this object found by Ogle. And the mass derived for this single black hole, as we assume here, is about 8 solar masses. So it's actually very similar to what we've seen in other black holes at the distance of 1.5 kiloparsecs. So this was found by combining, as I said, combining brightness changes and positional changes. This is the exquisite light curve from Ogle and other telescopes obtained over a long period of time. And this is the follow-up obtained with the Hubble Space Telescope. And this is, as I said, this is the milli-arc-second change of the position of the source, of the measurement of the position of the images on the sky over a couple of years. So measurement of this combined with the photometry gave us the mass of the lens, and hence we were able to conclude that this is the very first isolated black hole in the Milky Way. But moving on, I will now go to Gaia, which is my main topic in the work field, let's say. And I know that a couple of candidates here we already have from Gaia, especially Gaia 18AJZ. I will come back to that object in a second, where with the mass we estimate is about 12 solar masses. And there are two other candidates which are actually not even neutron stars. They're most likely white dwarfs, but I will mention them here as a preliminary work. So a couple of words about Gaia. So this is the launch. Gaia.
8, 7, 6, 5, 4, 3, 2, 1, top, décollage.
As you hear, the counting was in French, on December 19, 2015. And I remember we were streaming this launch from this very room when it was happening live. So we were big fingers crossed whether it's going to explode or not. But it has not. And it's been operating for the next 11 years. So this is an animation showing the launch. So that happened in French Guiana, of course. This is the European Space Agency mission. At that time, they used Russian Soyuz launchers, which were small enough for a mission like this and very cheap to run. And this is Fregat, which put Gaia into right orbit. So this is Gaia now unfolding the solar panels, and this is the fully expanded mission. That's how it looked. So it looks like a space flying saucer. So they do kind of exist in space. And here you see that Gaia actually was not orbiting the Earth like Hubble Space Telescope, for example, but it went on a journey, a month-long journey to L2. L2 is here, of the system of the Sun, the Earth. So the L2 is here, and so Gaia was revolving around L2. This is where James Webb is also residing, the map, and many other space missions. So this flying saucer was equipped with telescopes over there, and it was always shielded from space, so solar radiation from there. And it was rotating with a period of 6 hours, and then precessing its spin axis. So thanks to this, it was able to scan the entire sky, as you see here, with these two telescopes, many times. So on average, each part of the sky was scanned over the first 5 years of the mission. The nominal mission was scanned for about 100 times. There were parts of the sky observed more frequently. So this is the map of the sky constructed by Gaia. So after multiple scans, you can imagine that each of these dots, which is one of 2 billion sources, was observed multiple times. And Gaia was measuring its position, its brightness, changes of these parameters, of course, spectroscopy as well, and all possible astrophysical parameters. So kind of summarize it, the ESA mission launched in 2013. It was actually operating from July 2014 until January 2025. So fairly recently it stopped working. It was located in a 10 meter in diameter, It had 2 mirrors, 1.4 meter. So up to a point, it was the largest space observatory there. The depth of the scanning was down to 20 and a half magnitude, about 21 maybe in G band. So Gaia used its own band, essentially wide filter. And there were 2 billion sources of the entire sky scanned. Gaia was provided photometry, astrometry, and spectroscopy for all these 2 billion sources. And then the data is still being published through Gaia data releases. The most recent one happened, DR3, happened in June 2022. And then the next one will happen in December 2026, so in about a year time. And it will contain, for the first time, it will contain all time series of all products of all sources. So you imagine 2 billion sources having a time series of photometry, time series of astrometry, time series of spectroscopy, spectrophotometry, and everything you can essentially dream of. Because so far the data releases were containing some kind of higher order, higher level products like parallaxes, the main goal of this mission, by the way, and stellar parameters, proper motions, stuff like that. Now, after DR4, you will be able to dig into the data yourself and find stuff you really are interested in. As I said, so Gaia was mostly, its primary goal was to measure parallaxes and proper motions of these 2 billion stars. It's essentially a fairly straightforward parameter, but not so easy to get. You need an exquisite precision in astrometry to do that. So Gaia was using parallax effect going around the sun together with the Earth, and then measuring parallaxes and then hence distances. This is on animation. I hope you'll be able to see it, how it looks. Of course, it's sped up. So the stars which are nearer, they make these circles on the sky, which are larger, and then the further you go, the smaller the stars. So I think this kind of nicely visualizes that we can actually probe a large fraction of the Milky Way in 3D. And then on top of that, if you add the distance, you also add the proper motion, then you will start seeing that in a moment, that all the stars, they move in the Milky Way. So we were able to trace not only the spatial distribution of stars, but also the kinematic distribution. So essentially it's like 6D. This is the proper motion turned on. You see the stars are moving and all the constellations are actually falling apart. Yeah. So Gaia was scanning the whole sky in order to measure these parameters, astrometry primarily, but also because it was scanning and measuring brightnesses, it was possible, and this is what I've been mostly involved in when I was working at the University of Cambridge, we were able to identify things that changed, or things that appeared on the sky, or they went dim, or they changed in brightness. So here you see a map. You can see that. You can see the year, but this is scanning over time, multiple times, different portions of the sky, and you see these targets appearing. So while Gaia was scanning, we were digging into this daily data and looking for things which were new, mostly supernovae or other kinds of transients, but also stars that change their brightness, like microlensing events. So this is something what we call Gaia Science Alerts, and it's been running from the very beginning of the Gaia mission operation. Actually, so Gaia started collecting data in July 2014, and we started our first alerts in September 2014. And actually, it was a conference we've held about Gaia Science Alerts, and that one happened in Warsaw, actually at the University of Warsaw in Biblioteca, the library, where we announced that we found our first alert with Gaia. And it operated, the system operated until the very end of the operation, so mid-January 2025. Typically, the system detected between 10 to 20 new targets, so there were up to 20 alerts every day. In total, 27,000 alerts were reported. Main thing that it was all sky, as Gaia was scanning the whole sky, and it was completely unbiased. So we covered all science cases. We were not only looking for supernovae, we were not only looking for cataclysmic variables, not only looking for microlensing. So we actually looked for everything that was scientifically interesting. For example, we were not looking for variable stars, and I'm not saying that they're not scientifically interesting. Don't get me wrong, but there is no reason we should alert on a Myra getting brighter because it will keep doing it for forever, right? While supernova only appears once. So we might miss some interesting science opportunity if we don't alert on that supernova. If we alert on a Myra, then this opportunity will come back in a couple of months later. So there is no reason to alert on this. So the system had to weed out all the variable stars which do repeat, and then only alert on things which were transient. That's the word transient, what it means. It's just temporary. Here's an example of a star. You see this started in 2014. So the star was very bright, about 13th Mach, doing nothing for many, many years. And then suddenly, but still slowly, it was getting brighter. So this is, of course, with your eyes being trained in this very room for microlensing, you know immediately that this is a microlensing event. So this is the alert page, which we run at the University of Cambridge. So you see all the data. We were able to publish, actually Gaia Consortium allowed us, the Gaia Science Alerts system, to be the very first releasers of the data. Even before anyone saw any Gaia data, we were able to make the data public. So all these light curves were made publicly available to everyone, not only at the moment of the alert, but also way after the alert. So the 11 years long light curves are now, the 27,000 objects are available through that web. Why do we care about, in particular, about microlensing events? So this is, I'm coming back here to the astrometric part of the microlensing events. So, as I said, so Gaia is delivering, is about to deliver in year 4, but is measuring the astrometric time series for all 2 billion sources. So the thing is that with Gaia accuracy, we can measure the 1 millisecond displacements, something what has been done with Hubble Space Telescope only once successfully for the Hubble event. So here you see what's the accuracy standard deviation essentially of the measurements in astrometry depending on the magnitude. So everything all the way up to 18th Mach is measured with accuracy better than 1 millisecond. And actually many microlensing events happen at this range of magnitude. Even for fainter things, we can still have a decent accuracy. So this, as I said, this data will become publicly available in DR4, and it will cover data from 2014 until 2019. This is a quite complex plot from Chris Lipitsky, who's been working on this during his PhD and later. Just a comment that Gaia is not actually going to give us alpha, delta as a function of time, as we think, time series in astrometry. This is going to be alpha and delta, right, ascension declination as a function of time. No, it's going to be a bit more complex because Gaia is scanning the sky in 1 dimension. So this is the along scan dimension is going to be the one which has this accuracy. The across scan is going to be something like you typically get from space. It's still not bad, of course, because it's a big telescope in space, but this exquisite precision we can only get in 1 dimension. So this is what we call the along scan shift. So Gaia essentially measures how much this object in the current scan has been away from its original position. So if you see a trajectory like this is just a star. Every star does this kind of wiggle on the sky because it's a composite of the proper motion and the parallax effect. So if you see this star over a couple of years doing a trajectory like this, these are the scanning angles, right? The black lines. Gaia is only giving you the 1-dimensional measurement in astrometry along this direction. But the thing is that we get multiple scans at kind of quasi-random range of angles. So hence we're able to mathematically compute these parameters with fairly decent precision. But this is just a caveat to remember about that the Gaia astrometry is going to be 1-dimensional, yet it is still going to be very precise and again useful for microlensing. Here are some simulations we've done for how Gaia microlensing event might look like. So the magenta curve is actually the curve we've seen in the past. So essentially composition of the proper motion and the parallax, where when we add a microlensing component to this, it distorts the astrometric position. And in this case, you see the actual measurements along scan where they are placed. And here you see the residuals with respect to standard model with no microlensing, and this is the model with microlensing. This is the data, which is correlated with the peak of the amplification of the event. And the displacement is a order of 1 million arc second. So we are able to detect if this was a simulation of 10 solar mass black hole of 2 kiloparsecs. So if such black holes exist, we should be able to see them already now in Gaia data. And we are now studying this very data to make it available to you in next year. In Gaia free, so in 2022, we did a preliminary test how sensitive we are to microlensing. This only included photometric light curves like this. This is a Gaia light curve for microlensing events. And these are their locations. So the main feature here is that Gaia can probe the entire sky, right? So we see a lot of microlensing events in the bulge. Many of these denoted as B. They are actually oval microlensing events, which we then identified in Gaia data. So this is where most microlensing surveys they look for microlensing events. However, Gaia is scanning both southern hemisphere, northern hemisphere, the entire sky, and hence we probed microlensing events from all over the place. Even in obscure places like this, where there is essentially no background stars, we still see some microlensing events. So from this very limited data set, we found almost 400 microlensing events. One of them turned out to be particularly interesting. This one was very bright, found by Gaia only, and it showed a very significant signal of parallax. Microlensing parallax is essentially the same effect that because of different viewing angle, you can see the event changing. And thanks to this, you can measure the mass through this component here in this equation. I don't want to spend too much time on this, but we know one of these components which we need for the mass measurement. The other component is the Einstein radius. We will be able to derive it from astrometric time series, but there are also ways around it. So for this very event, Gaia 3 lens 001 was the very first in the catalog. We measured the mass doing some tricks. Without seeing the astrometry, we simulated the astrometry in order to reproduce the parameters Gaia gave us, and we found very good constraints. And we measured the Einstein radius and the mass, and we found that this is about 1 solar mass at 1 kiloparsec. So most likely a white dwarf, because we see no light from the lens itself. These are some other events from Gaia 3 studied by Katarzyna Kruszyńska in her PhD thesis, also later in her work in 2024. So there are some events from Gaia which were then supplemented by the data of Ogle and Moa and others. And then we used the code we developed mostly by Cornel Kobi in his work 2025, where we were able to include the priors on the Milky Way and then complement this equation here, complement the missing Einstein radius size with the most likely distribution of lenses, assuming the dark lens population behaves like the luminous components in the Milky Way. We were able to derive these masses for some of the candidates, like 6 solar masses, 3 solar masses, even 1 solar mass for this one. So there's a bunch of candidates. There are some events we did manage to solve, and I'll go through them quickly. I'm running out of time, I see. So this is Gaia 16 AYE, one of the most complex microlensing events ever found. So there was the alert, and then something funny happened. So this star was going up and down over a period of 2 years. And there's actually quite a lot of data from Ostrowiec itself, especially around here, around the critical curve, the cluster crossing were collected from our own observatory. So 20,000 observations from the ground were collected. And this is the model found by Schroeder and Bruce. And here we were able to derive both these components and derive the mass. Unfortunately, it was not a black hole, just a standard binary system at about 800 parsecs, boring binary system. But the thing, what we did with this event, we were able to publish Gaia 1D astrometry, and this is the actual Gaia data for this very event. So that was the very first data release from Gaia of the 1D Gaia astrometry, and we published this as a Gaia image of the week in 2021. Why was it interesting? Because this is the trajectory. This is actually what you see on the sky when you look at this event. So the lines are just to guide your eye, and the black dots are where Gaia observations are. And you see, because of this evolution of this event while it was lensing and binary the lens, you see very crazy shape on the sky. So this is what Gaia data is going to look like for this very event, and we did check that it does look like this. Another event, Gaia NCBJ, published by Katarzyna in 2022, turned out to be again 2 solar mass dark object. Another interesting event was high magnification event, and we found that this is about 1 solar mass at 5 kiloparsecs, so most likely a white dwarf. But here we even published 3 papers out of 1 event because we had such a great wealth of data. You see there is a lot of observations from a network of telescopes, but there is also data from Spitzer. We've managed to observe this event from 2 viewing angles. This is from Earth and Gaia. This is as visible from Spitzer, so the satellite which was located almost 2 astronomical units away from us. So that gave us a good perspective, and that hence we were able to measure the parallax. The spectra we collected for this one, and moreover, we were also able to derive to obtain the interferometric measurements. At the very peak of this event, we were able to see the images. You see these 2 images of at the separation of less than 1 millisecond, 0.7 millisecond. This is the smallest Einstein radius ever measured directly from the images, and also we could see the rotation of these images for the first time. Okay, another event I mentioned, 18AJZ. This one we like the most because it's the most massive one, candidate at least 12 solar masses at 2 kiloparsecs. And again, we have data from Gaia and Noble here, but we derive only the priors, we use the priors to derive the mass of this object, and we actually have some degeneracy, which we will then resolve next year with Gaia data. And again, that's another event I wanted to show you, Gaia 20 FNR, where we have, again, unfortunately boring binary system, half and half everywhere. But then for this one, we got the extruded data, soul spectra. It was a very long event, very bright one. So we were able to collect a lot of data. But from Gaia data alone, we wouldn't be able to derive anything because we just looked at 2 peaks. Fortunately, we had a network of telescopes at our disposal. We collected additional data, so hence we were able to trace very interesting features of this light curve with this data. Moreover, this event happened to be observed by TESS, so we also have TESS data around this peak and somewhere there. It was observed by NEOWISE infrared telescope, and then also we collected some SWIFT data. So everything from ultraviolet to infrared we collected on this event. So combining this with Gaia, this event was observed by 4 satellites. So the work is in progress. This is the solution for the binary lens. This is the Gaia astrometry, how it's going to look like in Gaia data in DR4 and then DR5. It's going to be very complex. So Moritz he's working on this project as we speak. So in my last couple of minutes, right, I will talk you through the activities which kind of resulted from all these Gaia activities and Gaia Science Alerts in particular. I will talk about the global telescope network we built for Gaia Alerts in 2013. As you could see already from these results, we needed very dense photometry for most of these microlensing events, but not only. For all the other kind of temporal events, you needed a reaction system and react for events which happen on both north and south hemisphere. So we've constructed a network of telescopes Currently, the network comprises 150 telescopes, different sizes from 5 centimeters to 2.5 meters. Most of them are professional, but also now we're expanding this network with amateur and school observatories and outreach facilities as well. Now these are very good times for these amateur telescopes because they are the good quality instruments are available for fairly decent prices. And these people can actually, they're very skilled observers, but also they can get involved in observations at the professional level. Many of these telescopes are manually operated, like the one we have in Ostrowiec, but also there are robotic ones. I'll show a couple of examples in a second. If we zoom in here in Europe, we see a lot of these telescopes. Actually, historically, they were built there. We have one telescope next to London, which is 100 years old and is still operating. It mostly is a teaching facility, but it is contributing a lot of data for our work. But the weather there is, of course, like here today. We also have telescopes in Lithuania and Norway, but also the entire Mediterranean region is covered with telescopes, which are contributing to our observations. Most of them are volunteering, they observe in time, so whenever they can, which happens very rarely, especially in northern parts, but whenever they can observe targets we propose. So for some of them, we apply for time. There is an observatory in Loiano, for example. We've been in long-term collaboration with actually students from this observatory. We're going observing to Loiano for a long period of time. I'll just mention it here that we're expanding this link between amateur and school outreach facilities connection to professional observatories through a foundation. We founded earlier this year. This European Astronomical Society of Small Telescopes, which is actually it's called Citizen Science. We're trying to invite non-professionals to get involved into professional activities, especially related with small telescopes. So a couple of slides showing the telescopes. This one you know. Hopefully it will start operating soon and we will be able to use it again for this research. So this is a 60 centimeter telescope next to Warsaw. This is another 60 centimeter, but this is an Italian robotic telescope in La Silla. So this is fully robotic, fully robotized, and we can control it from our computers while sitting here. We work with a 70 centimeter telescope in Ukraine since 2015 already. Of course, there is a network of telescopes we collaborate with closely. As Comprising Observatory, they have already 1 meter, 2 meters, and 0.4 meter telescopes everywhere. So we use their time quite a lot. Other examples include Chorzów Planetarium. It's a refurbished planetarium and observatory, so they have a 70 centimeter robotic telescope. Not the best place for observations, of course. As you can imagine, it's the center of the city. However, still, it is acting as an outreach facility, but then during the evening it switches to a robotic mode and it's delivering scientific data during the night. This is another school observatory built by a director of the school in Bolencina. So this is 40 centimeter, fully robotized telescope south of Poland, close to Bielsko-Biała, where again this acts as a teaching facility or just for fun for the kids during the day, and then during the night it is delivering quite a lot of significant high quality data. There's also a growing number of smart telescopes these days. Some of them have 12 centimeter telelenses, but there are even small things like 5 centimeter telelenses. Cheap, decent quality, and they are essentially operating from your phone, where you can actually point it to some nice images. They're built for astrophotography primarily, but we are now investigating how can they be used in some scientific activities. And actually the first tests are quite promising. They can deliver data of fairly decent quality. Well, the thing is that there's a lot of them. You see a map of one of these networks. So of course you can see where rich people live. So Europe, US, and Japan. But we're talking about tens of thousands of users potentially getting involved in this kind of observations. I just mentioned that we've been organizing a series of workshops related to small telescopes, networks, but also Gaia alerts, essentially continuously since 2010, where we started in Cambridge. We had 2 of these workshops held in Warsaw. In 2014, as I said, we announced the very first discovery of our alert. And last month, we actually had a meeting in Tenerife. So we keep going, and we do them in very nice places, as you see, especially recently. Okay, just to wrap up, I'll just advertise the system we built for these small telescopes, which is called BHSTOM. It stands for Black Hole Cardinal Observation Manager. And this has been done in cooperation with Astronomical Observatory people. They have a lot of experience. So this is a web tool, free of use, and it's funded through the European grant now. So it is dealing with the time domain observations. It processes the images, does automated standardization, and queries the archives. So the data flow goes like this. There are the targets. Users say, okay, I want to monitor this quasar, or I want to observe the comet, or a supernova there. So they send it to BHSTOM, and then we communicate with the network of telescopes, and then we get data back from them, and we process the data. We query these archives. There is also all the archives being queried for these targets, and as well as radio. And then what we bring back to the users is the science-ready data products. So essentially, they get light curves of the objects they requested for, depending on the cadence they wanted. Multi-band and photometry is delivered back to them. So we see we make the users to stay away from these telescopes. So they don't need to write any proposals. They don't need to process any data. They just request a target, and then we deliver the data for them, so that they can focus on the publications. Everything can be scripted, of course. All this data flow here can be completely automatized. If the telescopes are robotic, then this whole flow, maybe except of writing publication, is automatized. This is just a slide showing that we do the image processing for all, uniformly for all 150 telescopes, and we standardize it, and it's downloadable forever. A couple of examples of light curves. This is a supernova. The different colors denote different filters, not different telescopes. So you can't tell the differences in here. Same here for this light curve of a microlensing event with the planetary anomaly here. So this is all standardized like that. I'll just announce that we are also working on the comet. You will hear more about it from Fraser next week. This is the data, the light curve of the comet, the famous comet. I'll just stop here. We write papers on different topics. This is like 20 papers or so on different topics, starting from microlensing, of course, but also for supernovae, tidal deception events, all sorts of different things, and there are more papers coming. So in my last animation, I'll show the where microlensing events were found by Gaia in DR3. It's of course exaggerated, they don't look like that. And I'll stop by showing the movie of Gaia leaving the orbit. Cut the volume, and I'll stop here. Thank you. Here. So Gaia was kicked out of its orbit in L2, and is essentially leaving the L2, but it's staying on the solar orbit. It's actually a very nice tool. This is all real data, Gaia Sky, that's named. So you can have the entire trajectory of Gaia. All the other things. So see, it's leaving the orbit, it's kicked out in around early April. Now it's speeding up. So it's staying behind. And then the next one will show you when are we going to meet Gaia again. So, 2059.
4 little dots. Thank you. Thank you much. Thank you. And after 20 years, you're still doing a great job. So congratulations. Any questions, comments? Łukasz, maybe I'll start. I wanted to ask about the smart telescopes, the 5 centimeter ones. Okay, it's great advantages that they are like accessible to many people, but how can they contribute really to the photometry?
Yeah, you have to be careful, of course, because they are built for astrophotography, right? So they have, for example, they have filters built in which cut the light of the light pollution, right? So you can take your telescope out here in the middle of Warsaw and take a nice image of a nebula, right? But they cut out some wavelengths of where most of the lights is emitted. So, and that screws the photometry, right? If you want to do proper photometry, then you cannot do that. Then there are some AI algorithms built into this image processing, where they also, interpolate between pixels and so on. You don't want that. So, but if you can force these telescopes to work in the very raw mode, so essentially just measure the pixels as they are, and they have, these are modern CMOS cameras, so they have sensitivity, they have pixel scale you want, they have filters built in, RGB, but still you can kind of calibrate. So if you do some tweaking, then you can make them useful for photometry. We've been able to observe targets as faint as 14th magnitude.
Okay.
With the 5 centimeter telescopes.
With a precision.
Of order, well, decent one, but less than 10%.
Since you observe so many transits and stars, do you have any candidates for, like, say, black hole formation, like a star that is there, but just like disappears?
Yeah, we've been thinking about that, if we can do that in Gaia, but I think first of all, the rates for these are very low. So, and also with an instrument like Gaia, it's sometimes difficult to tell whether the star has disappeared or we're not having the data, right? Gaia was scanning so it was not taking images, right? Gaia was processing the images on board and then delivering the measurements down to us. And sometimes in the hard drive of Gaia was only 800 gigabytes, right? So it's much smaller than your laptop, right? So sometimes they had to delete some of the data. So sometimes we were not receiving an observation, even though we knew it was supposed to come. So we would trigger as the star has disappeared, but that would be essentially a technical reason. So that's why we decided not to look for this. You can possibly do that yourself now with the forthcoming DR4 data. Essentially, you'll have the whole sky, and if you design your own clever algorithm, you can look for these. I know people have been doing this with HST, different galaxies, other galaxies, right?
Yeah, those are some candidates.
There are some candidates, yeah. But no one looked for these in Gaia yet. So there's still an open avenue. Mm-hmm.
All right.
So, due to observational biases, we were only able to detect so far this Gaia black holes on some specific periods that were relatively wide. With the new data released in 1 year, will we be able to discover black holes in a much wider orbital spectrum?
Yeah. So the black holes we reported on, PH 1, 2, and 3, actually they were found so easily. They were just jumping at us in the data. So we had to publish them, right? We had to get some special permissions to publish them before the data release. But since this was a perfect showcase, that's why we published them. But in DR4, there's going to be a special catalog of black holes published, and that will contain dozens of systems like this, of different masses. So you will have a lot of work to understand all these.
That's a secret.
Sorry.
But be prepared.
Yeah, be prepared.
See me now, right?
I have an artistic question. As you said, the movement of the source position is measured in milliarc-seconds, and with our almost perfect line. People still keep showing animations where the huge star fields get heavily distorted when the black hole is going through. Don't you think it's too misleading for the general public?
Yeah.
Because usually those artistic impression, artistic view of some objects are more or less probable. But this is completely fake.
This is fake, yeah, I agree. But this is actually, on the other hand, this is so complex to show, to explain. I think microlensing and lensing in general is one of the most complex phenomena to explain to lay people, popular citizens, right? So if you exaggerate it, then it makes it visible and people can start feeling it. And only then you reveal that it's all fake. Yeah, I agree. It looks nice though.
Yeah, sure.
Martin?
Yeah, I was wondering, it will be possible to see how many black holes are just solitary, or how much are in binary system. I think you will see this, but it could be very good to know this.
Yeah. That's why we take these multiple approaches, right? So with microlensing, you can probe this single black holes probably only through microlensing, right? There's no other ways of doing it. Binary black holes, well, binaries with one luminous companion, right? At least these. We can probe with astrometry, and there's going to be a lot of the results coming from Gaia. Binary black holes with black hole, this is difficult again, right? So here you probably need to rely on microlensing again. This is difficult, but yeah, I agree. Now, once we will have the entire Gaia, uniform Gaia data, we will be able to derive these statistics. Even if we find a couple of examples, we will then understand the experiment, so all the efficiencies and so on, everything can be derived. So for the first time, we will be able to say anything about this problem, at least in our vicinity in the Milky Way, of course.
There's
Just quick question. When Gaia is kicked out from L2, will it still taking data?
No, it's just switched off, essentially.
It's just switched off, but it's like technical reasons. Like I understand that the fuel, it runs out of fuel, but like can still collect.
Well, the thing, Gaia was operated in the drift scan mode, right? So there's the CCD, this huge 1 meter CCD, which was constantly reading, right? And the readout time was perfectly aligned with the spin. So you have to control the spin very accurately so that then it matches the readout time. If you don't have fuel, and you are not able to control the spin, because so the fuel was used for the microthrusters, and every time Gaia was hit by a micrometeorite or something like that, or slowing down here and there, so it was immediately fixed. So we were, for 11 years, we were controlling Gaia spin down to really obscene precision. Now we cannot do that, right? So we cannot even control where it's pointing. That's one thing, but then we cannot control the readout at all. So there was no point. Yeah, many people thought about it. What can we do with such a great observatory? But unfortunately, maybe in 2039 people will come up with some ideas.
I can see there's one more question from Zoom. Marius. Hi, Marius.
Oh, yes. Hello, Milena. Hello, Łukasz. Thanks.
Hi.
Yes. Thanks for nice presentation. You Łukasz, forgot to mention extremely long microlensing event Gaia 19 DKE. Yes. Yes, and in one of your slides I saw that it is the Gaia data released 4 will be from 2014 to 2019.
Yes.
And so question it is, in that paper we predict that will be some astrometrical shift. But due to the alert of Gaia 19 DKE, so alerted was in 19.
Yeah.
Or data astrometry data will be from 2013 to 2019. So do we check or we will see the in data released for this astrometric shift or not?
Yeah, I know what you mean. So if Gaia 2019 DKE event is going to be included in the astrometric part of Gaia DR4, unfortunately I checked that so that the event was discovered in late 2019, and it peaked in 2020. So it is outside of the DR4 window, unfortunately. So there is not much data we expect in DR4. Sorry.
Okay, wait, DR5.
DR5.
Okay, thanks a lot.
It's 2030, so be patient.
Okay, thank you. Thank you, Mariusz, for asking the question. Thank you, Łukasz, for a great presentation. Congratulations. And we meet here next week to listen to Fraser from NCBJ, who's going to tell us about his research on comets, right? So with beach tunnels. Thank you very much.
Włączyłeś? Włączyłeś. To mogę włączyć.